All right, my friends, let's see what we can do about section 9.1 part 2. This is still intro to conics. It's just a little more about what you should know about parabolas. Just a note to you, I know it's been such a long time since we did section 9.1 part 1, where we were talking about how to graph parabolas with 5 points of accuracy, whether they opened vertically or horizontally, and then also throwing in completing the square into that process. If you don't remember how to do that stuff, it would be a really good idea for you to go back and review those notes. Make sure that you've done the problem set that I assigned from that piece before you try to follow along with this video. There's no shame in stopping this video, going back, building yourself up to be ready to hear what I have to say, and then coming back and playing the video. Also, let's get started on a warm-up. So the warm-up for this lesson would be graph the quantity y plus 5 squared minus 12 times the quantity x plus 2 equals 0. Okay, also, when you watch my videos, I will not give you a long time, I will not have long pieces of time where you can work ahead and do the problems. Instead, I would just encourage you on every warm-up and every example that I give, just pause the video, see what you can do with it on your own, and then push play to see what I do. Okay. So for this problem, there's so many ways to do it, but I would recommend that you not expand any quantity squared because those are perfect golden little nuggets where you don't have to complete the square. They did it for you. So whatever you do, don't expand this out. And then I also wouldn't recommend expanding this piece out. You're just creating work for yourself if you do. So I would actually personally move the 12 times the quantity x plus 2 over to the other side of the equation. And then this 12 here is a stretch factor. And remember, because of our training, which side of the equation do we prefer our stretch factors to be on? And the answer is whichever side has a squared term. So you're going to see me divide the 12 over, so it can be over here with this squared term. So we'll divide the 12 over. We'll have 1/12 times the quantity y plus 5 squared equals x, the quantity x plus 2. And I'm going to point out that that is inside a function by putting a very redundant first power there. A previous habit would be for us to subtract the 2 over, but remember that if you leave your addition and subtraction inside functions where your coefficient of x or y is 1, then you can actually use kind of like counterintuitive shifting rules to figure out how a parent function was shifted. So whatever our parent function is, it would have been shifted down 5 and to the left 2. And I can tell just by looking at this form. Now let's talk about what is your parent function. If you were to strip off the shifts and kind of take off, if you want the stretches as well, you can tell what your parent function was. It would have been a y squared equals x or x equals y squared parabola. And which way would that one have opened? And if you forget, you could just t-table it out real quick, but it would open to the right. And then now I've got this stretch factor of 1/12 on it. So we are going to come back and add a little bit more to things beyond this warm-up. So because of that, I think we are all going to be happiest if you go, let's see, go from, on the y-axis, go from positive 1, 2, negative 11, and then on the x-axis, go at least from negative 5 to positive 5 or so. Okay? All right, you don't need all that space to graph this, but we're going to come back and add some more stuff in a little while to this one. So where did we say the vertex was? So shifted down 5 to the left 2, so it would be at negative 2, negative 5. And then we decided it would open to the right because it was an x equals y squared parabola, and it just has a positive stretch factor, so it's still open to the right, but it's going to be really shallow. So normal y equals x squared maybe would have looked like this, but this one's going to be like pretty wide there. So from here, let's get some points of accuracy from your vertex. If we went up or down 1, you would go to the right, not 1, but 1/12 of 1, or 1/12, so not very far. From the vertex, if you went up 2 or down 2, you'd normally go to the right 4. And so 1/12 of 4 is, what is that, 1/3? Not very far, again. I don't know about there. And so what I think we should do, just to get something that's not so, hard to get accuracy out of, let's try going like from the vertex, let's go maybe like up 6. So we would go to the right 36, and 1/12 of 36 is 3. And then the same thing, if we went down 6, that's what that negative 11 was for, then we could go to the right 3. And then we'd have a little more accuracy to aim for, which is kind of nice for this one. There we go. Something that looks like that. Okay, so this is, after part 1, this is something that's supposed to be very doable for you. Now, not really part of the warm-up, but I do want to give you an idea as to kind of what the new stuff is going to be. In this lesson, we're supposed to also, in addition to being able to graph this stuff, we're supposed to, typical directions would be find the coordinates of the vertex, which I think is already in our wheelhouse, but they also want you to find the coordinates of what's called the focus, and they're going to want you to find the equation of the directrix. Oops, directrix. There we go. Okay, so these are going to be, this is what we're going to really focus on in this lesson, is doing these two things. And we can come back and add this in after we've had a chance to talk about theoretically, why do you do these things the way they do? What is the focus? What is the directrix? And, why do you do that? So I'm not going to show how to do this quite yet. I'll come back. It's going to be really easy. The thing that's going to take the energy is following the derivation that we're going to do. And let's get started on that. So in order to explain focus and directrix in a really, thorough way that should satisfy your curiosity and all that stuff, you're actually going to go all the way back to a definition of what a parabola is. And there are many ways to define a parabola. Okay? We talked in class about, you remember when I got those 3D cones out and we were talking about in 3D space, what's the definition of a parabola? It was the intersection of a double napped cone and a plane, so that the plane was, parallel to one of the sides of the cone. And so there's a definition, but that's not the one we're looking for. Here's the one we're looking for. We're looking for the definition of a parabola on a two-dimensional plane. So what makes this point be on a parabola as opposed to this one? So this one is part of the parabola and this one isn't. And so there's a way to define all these points that are so special that are on the curve of the parabola. And it actually has to do with these two words, focus and directrix. So let's get started on that. What makes those points be on the parabola? So a parabola is the collection of all points that are equidistant from a fixed point. Well, that's not how you spell fixed. Okay, a fixed point. Any guesses as to what the fixed point is called? Called the focus. We'll underline that since it's a definition within a definition. And a fixed line. And guess what that fixed line is called? Called the directrix. There we go. Okay. And it's okay if that looks like just a bunch of crazy words, because we're going to do an activity that should help you to make sense of what we are saying here. But understanding this definition is going to be very key to making this lesson really easy to get through. Okay, so take a minute and read that definition for yourself one more time. And for the next activity, and this is just the beginning of a derivation that we're going to do, for the next activity, you're going to be probably happiest if you've got a straight edge. If you can, a ruler type straight edge, but, even the side of an ID card or a folded up piece of paper would work as well. Okay, so with that said, we are going to draw a parabola based on this definition. And to do that, what you do is you actually would start with the fixed point called the focus. Let's see, you can follow my lead with spacing. So I'm going to put a focus here. So it's just a fixed point. So I will say focus, you will live here. And then you can also draw the directrix, a fixed line. Now, where you draw the directrix is going to affect which way your parabola opens. So I am going to draw a horizontal directrix that is below the focus. If you chose to do a vertical directrix or a diagonal slanty type directrix, or if you put a directrix above the focus, it would affect which way the parabola opens. If you move the directrix closer to the focus or farther away, it would affect the stretch on the focus. So without being super scientific, I'm going to make for this example, and you probably want to follow my lead because we're going to use this for derivation. I'm going to put the directrix below the focus, and I'm going to do my best to make it look horizontal. That looks kind of horizontal to me. If you have lines on your paper, then you are worlds ahead of where I'm at. But I'm just going to go ahead and draw. I'll make it dashed because it's just actually a graphing aid for the parabola. Now that I look at it, it does not look horizontal at all, but we'll pretend. Okay, so here we go. This is going to be my directrix. Okay, so the next thing that we are going to do is reread this if you need to, but we're going to start finding points that are equidistant between the focus and the directrix. And the first one's going to be the easiest. You could measure if you want or not, totally up to you. I like to just eyeball it, to be honest with you, because it can get to be kind of annoying if you measure each one. But there is right there, that's one point that is going to be on our parabola. And how come? Because this distance is the same as this distance. And I'm just using those little geometry congruent marks to indicate that. Okay, so now let's talk about the harder points to get. All the rest are going to be the harder ones. So remember that the distance between a point, maybe about here. Okay, the distance between 2 points is just the length of the segment that connects the 2 points. But the distance between a point and a line is the length of the segment that connects the point and the line, but is perpendicular to that line. So this is going to be a little interesting as we go out to try to get those two distances to be the same. And, I can tell you right now, if I measured those would not be exactly the same, but I'm trying. So that's all. And this is kind of a concept pick. So you're trying to make these distances equal each other. And then you could always kind of like copy yourself on the other side, once you've got, teacher trick. Make your dots globbier if things aren't working out for you. Okay, so these 3 points would be points that are on my parabola. The focus is not actually on my parabola, but you could go out wider to get more. It gets harder the farther out you go to make sure that your distances are the same, but it's kind of fun. So you're just trying to make sure that those distances are the same. You could go like way out there. Again, the farther out you go, the harder it gets. Okay, this is probably a disaster. But pretend that those are 1, 2, 3, 4. Okay, pretend that those look the same. There we go. And we could be here forever and ever and ever because there are infinitely many points that are on each parabola. But I would recommend that you just do, usually 5 points gives you enough to aim for. And then when you fill it in, anything that's along your path, hopefully would be something that also would be equidistant from your focus and your directrix. There you go. So now you have a new fun way to draw a parabola. And if you ever get bored, or if you have a younger sibling that you need to keep busy, you could always play with that challenge of drawing different ones. Okay, but there you go. Now you know how to draw a parabola based on this definition that we have written. Okay, and hopefully your picture is nice and big, not too shrinky-dinky, and looks something like this, because we are actually going to springboard our derivation right off of this picture. So let's get going. What we're going to do here is, to keep our derivation simple, we are going to superimpose an XY plane onto our picture that we have here. And we are going to make it so that this point right here, and I hope you're okay with that being the vertex, what I'm going to do to keep this derivation as simple as possible is I'm actually going to make that vertex be at the origin. So, boop, boop. Okay. Okay, and so this is the x. This will be the x-axis. And then again, because I'm hoping to make the vertex be at the origin, I'm going to draw the y-axis so that it goes through the vertex and the focus. And I guess I don't need all this. There we go. Okay. So now that we've got this picture drawn, the next thing that I need to do is make sure that you are going to be okay with this letter that's going to come into this story. So the letter P, when we use the letter P when it comes to parabolas, it's going to represent the distance between the vertex and the focus. And because of how this was drawn, you could easily take the word vertex out and replace it with directrix. Like that. Okay. Okay. So since P is the distance between the vertex and the focus, then we could actually add some coordinates to these things. We made sure that the vertex would be at what point, and that was by design, just so this would be a little easier. So the vertex here is at 0, 0. The focus for this would be, so think about it, if P is the distance between the vertex and the focus, then what would the coordinates be at this point right here? They would be 0, P. Awesome. Okay, so we're really just getting set up here for a derivation. Now I want you to think about, what would the equation of this directrix be? It's horizontal, and the distance from the vertex to the directrix is P. So what would the equation of directrix be? It's horizontal, so it'd be a collection of y coordinates, or a collection of points that all have the same y coordinate. And what would that y coordinate be? So the distance between the vertex and the directrix is p, but you went down, and so it'd be y equals negative p. Good. Okay. Next thing, what we're going to do for the derivation is we're going to define, it's if you have a point that's on the parabola, what's so special about that point versus a point that's not? So we're going to, in our derivation, we're going to define what's the special relationship between x and y that makes something be on your parabola as opposed to not. So go ahead and put a generic point xy somewhere on your parabola that is one of the points that's on your parabola. And then let's talk about why is it on the parabola and as opposed to not. So let's see. Okay, so okay, well, it would be that this distance right here, I'll call this distance 1, would compare how to this distance right here. I will call this distance 2. And what's the answer? The answer is that these two would have to be equal, right? In order for this to be on the parabola. So we're going to use the distance formula, and if you don't remember the distance formula for the distance between 2 points in a plane, you'll want to go look that up so you're comfortable. But we're also going to need some coordinates for this point right here. So what are the coordinates of that point right there? Well, we went straight down from the point xy, so I claimed that it would have the same x coordinate as the point xy. But you're on your directrix, so what would the y coordinate be? It would have to be negative p. Okay, this is going to take a while, so put on your patience pants. I'm never going to require that you can show me the derivation. However, people who do the derivation are way less confused about why things are the way they are. Okay, so let's get started on that. What's so special about this point as opposed to something else in the xy plane? It's simply that these two distances equaled each other. So the derivation for the equation of a parabola would start by simply saying that that distance 1 has to equal distance 2. Like that. Okay, now from there, we're going to use the distance formula. So for distance 1, we're going to use the distance formula using just expressing the distance between xy and 0p. So distance 1 would be, we would do the square root of, let's do x minus 0 plus y minus p. And then distance 2 would be x minus x squared plus y minus negative p squared. Okay. Now, if we were in class, then we would pass this around and make people help me simplify this. But I'm here to tell you that they could have told you that this is the equation of a parabola and we all have to memorize it. And I'm so glad that they didn't, because this is going to simplify down and be super adorable when we're done. So let's think about what are some things we could do to clean this up. And the first thing that a lot of people want to do, I'm pretty sure, is get rid of the square roots. And in this case, that would be super easy. You could just square both sides of the equation, or you could figure if these expressions are equal to each other, then the radicands must equal each other. So either way, you could actually get rid of the square roots pretty quickly. And then in the same step, you could just write things a little simpler, like x minus 0, for example, is just x. So we're going to do that. So we'll have x squared plus y minus p squared equals, and x minus x is just 0. So on the right side, we just have y plus p squared. And again, I did just square both sides to get rid of the square roots and then simplified underneath. Okay, now for a little fancy footwork. This definitely gets worse before it gets better, but it does clean up super nice. We're going to expand out the squares. Oh, my equal signs aren't lined up. Oh. Let's try that again. There we go. All right, this is about as bad as this sucker gets. Now I want you guys to look at this equation and look for something that you could group together or simplify. And a lot of people would notice that you could simply subtract y squared from both sides, and you wouldn't have to show it, but it would explain why in my next step the y squareds will be gone. And then similarly, you could subtract p squared from both sides, and then that would explain why those will be gone in my next step. And then what else could we do? And we're almost done, believe it or not. What else could we do to simplify this just a little bit? Let's say we could add the 2py over, and it won't vanish, but it would at least group those together. So let's see what we would then have. We would have x squared equals 2py plus 2 more py's would be 4py. And then the book would have you work from this form, but because of our training, where do we like our stretch factors to be? We like them to be on this side of with the squared term. So I will deviate from the way the book explains this, and I will divide both sides by 4p. And then you'd have y is equal to 1 over 4p times x squared. Okay, now if you think about what we just got, this is what it would be like if your vertex is at 0, 0 and your parabola opens upward. And basically what we found out is you'd need to know two things in order to be successful here. You have to keep in mind what p means in order for this to make sense. Remember, p is the distance between your, I'm just going to say vertex and the focus. And then you'd also have to know that if you're solving for p, you just take your stretch factor and you set it equal to 1 over 4p. I think that's pretty great. Okay, so let's kind of generalize this so that you could have a parabola opens upward, downward, to the right, or to the left, okay? And then we're going to go back and finish that warm-up problem, do a couple examples, and then we'll be done. Okay, so if you have something like this, this would be where your vertex was where? It was at 0, 0. And this could be for if your parabola opens upward, which in our case it did. Or think about if p was a negative number, and I know I used p to mean distance, but the truth is, I guess I should fix that. The absolute value of p is actually the distance. P could be a negative number, okay? If your p-value is positive, it would make your parabola open upward. If your p-value is negative, it would just cause a stretch factor to be negative, so it would make your parabola open downward. So this would be your situation if your vertex is at 0, 0, and if you open upward or downward. So now I want you to think about what would the equation be if your vertex is not at 0, 0, if it's at some other point, which I'll just go ahead and call hk, but it still opens upward or downward. Well, if you are shifting your graph, let's say to the right h and then up k, then instead of y, you'd have y minus k. I'll just say to the first power. You'd still have 1 over 4p, and then how would you shift something to the right h? You would have x, and then you'd, like that. And I hope you don't think of this as something to memorize. I want to keep your memorization low. These are just shifting rules that you know. The new thing is really just what p means. Absolute value of p is the distance from what two things? Yep, from your vertex to your focus. And then to find P, you just set your stretch factor equal to 1 over 4P. That's the new stuff. This is just making you hopefully feel comfortable with different situations. Now, what would your equation be if your parabola opens to the right or to the left? Well, instead of y equals your stretch factor times x squared, you'd have x equals your stretch factor times y squared. And I know we didn't derive that one, but the derivation would have been so repetitive that I'm not going to go through that process. Now, where would the vertex be for that situation? Yep, at 0, 0. And then if you wanted the vertex to not be at 0, 0, if you wanted to shift it to be at some point hk, still your parabola opening to the right or to the left, then how could you do that? Well, you would have x, and then you would subtract that value there. Oops. First power. And then you could substitute y in for y minus k. There we go. So you would have shifted it to the right h and then up k, essentially. Okay, so this is kind of the general idea. Now, if we were to go back from there, if we were to go back to our warm-up problem, then you could finish it out pretty easily. And I hope after that grungy derivation, you can see how simple this is going to be. So it says find the coordinates of the vertex, which we've known forever. So where's the vertex? It's at -2, -5. Now, to find the rest, you're going to need to figure out what that p-value is. And how do you do it? You take your stretch factor, which remember, we always move to the coefficient of the squared term. And so you're going to take your stretch factor and set it equal to 1 over 4p. And then you just solve for p in whatever way makes sense. So you could use cross products, or you could just notice 12 would have to equal 4p. Therefore, p would have to equal, 3. Okay? So now you can actually go from your picture, and pictures are going to be very important to keep your memorization low. So this is the point -2, -5. And then after that activity where we drew one based on the definition, I hope it makes sense that your parabola will always open toward the focus, which is why it's called the focus, because your parabola is focusing on it. So from your vertex, we're going to go from there in 1, 2, 3 units. And what point is that going to be? That's going to be your focus right there. And what would its coordinates be? It would be, instead of -2, we're going to be at +1 now, and then still at -5. So your focus is at 1, -5. And where would your directrix have been? It would have been, in this case, it would have needed to be a vertical directrix. I hope that makes sense. If not, let me know. I can do a supplemental video. But from here, you're going to need to go 1, 2, 3 to the left, and then draw your directrix in. There we go. And so your directrix would be, it's a vertical line, so this would be a collection of all points at the same x-coordinate. And what would that x-coordinate be? You went to the left 3 from this point right here. So that would be x equaling -5. So your directrix would be at x equals -5. There we go. Boom, boom, boom. All right, my friends, moving to example 1. I hope this is making sense so far. Example 1. Find the vertex, focus, and directrix for 5 times the quantity y minus 1 squared equals x plus 3, which they probably wouldn't have those parentheses, but I went ahead and added them. All right, my friends. So I am a graphing person because I'm not a fan of memorizing extra stuff. So I personally would think graphically about this one. So what's your parent function or parent relation? It would be x equals y squared. Which way does that open? That opens to the right. What's my stretch factor? It is indeed 5 because it's on the squared side already. So I could graph it in just a couple seconds. So let's see, where's the vertex? It would be at negative 3, 1. Okay, that 5 is my stretch factor, so I would go up and down 1, and then to the right 5. And then up and down 2, oh boy, and then to the right 20. I think in this case, we'll just say that's what arrows are for. Oops, misplaced that guy. Really misplaced that guy. Ooh. There we go. Okay, so here's my equation, or sorry, my graph of my parabola. And then we could figure out, okay, well, let's make it official. Where's the vertex? It's at negative 3, 1. Where would the focus be? And that's where the picture can be really helpful. So how do we find it? First of all, you could set 1 over 4p. Where do I want to put that? It's because we want to also find the directrix. Okay, so we'll set 1 over 4p equal to stretch factor, which would be 5. You could multiply both sides of this equation by 4p. And then divide the 20 over. So we have a pretty small p-value this time. So remember what p means. The absolute value of p is the distance from your vertex to your focus. So that means that if you go inside the parabola 1/20th of a unit, which I know that this is more than 1/20th of a unit, or if you go back 1/20th of a unit, you'd have the directrix. So where would the focus be? It would be not at negative 3, but 1/20th of a unit to the right of negative 3. So what would that be? Negative 2 and 19/20ths, but still at 1. And then the directrix would be x equals, what would that be? Negative 3 and 1/20th, right there. And then that would be, okay. And a lot of people are wondering, like, do I have to draw the picture? You don't. So if you can visualize it in your mind's eye and then get all of these answers, then that is fine also. But if you ever get stuck, the picture is there for you. And I'm here to tell you, a year from now, when you're having to go through this in Calc BC and apply calculus to it, you're probably going to be drawing those pictures because a lot of the little details that otherwise you'd have to memorize will probably be buried under more current things. Okay, example 2, find the vertex, focus, not and, but directrix, and what's called the axis of symmetry for, and let's give you a challenging problem this time, y plus 3x squared plus 30x plus 68 equals 0. This is definitely the kind of problem that I think you should pause and figure out before you just watch me do it. With that said, I'm going to go ahead and get started. So what I would do, my friends, is keep the x terms on one side, and then I'm going to move the non-x terms to the other side. So I would have 3x squared plus 30x, and then on the other side of the equation, I would have negative y minus 68. Okay. Next, I'm going to factor out the leading coefficients. Remember that in order for shifting rules, vertical or horizontal for that matter, your coefficients of x and y have to be 1. So when you get to this step, you're definitely going to need to factor out any leading coefficient. I'm going to put that off on the right side. I'm not going to do that quite yet. Okay, now let's think about what's the magic ingredient inside these parentheses to get a perfect square. Let's divide the 10 by 2 and square the results, and we're going to get 25. I'm going to underline it to show that that's new. And then what did I actually just add to this side of the equation? I actually added 3 times 25, and I could subtract 75 off on the same side, or I could add 75 to the other side, and that's why I put off factoring that out. Anyway, so this is me adding a fancy version of 0 to the whole situation. Okay, so on the left side, I now have 3 times the quantity x plus 5 squared, and on the right side I have negative y, and what is negative 68 plus 75? It's negative negative 7? No. Oh, it's positive. Positive 7. That was hard. Subtraction's hard. All right, so now that I've got this, let's think about, where do you want the stretch factor to be? I want it to be on the squared side. So now, this is where I personally would maybe factor the negative out over here, but then divide it over, or multiply it over, however you want to think of that. So, and I'm also going to trade places with the 2 sides. So I'd have y minus 7 to the first power equals negative 3 times x plus 5 squared. And there's probably a little bit more of an efficient way to go about that, but there you go. Okay, so now let's think about if I was to graph this, and you will see me graphing these quite a bit, so I don't have to memorize as much. So what would the graph be? Which way would this parabola open? Its parent is a y equals x squared graph, so that means it would either open upward or downward. Your stretch factor is negative, so that means it would open downward. And then where would its vertex be? It would be at negative 5 and positive 7. Okay, we're just going to make this kind of a sloppy concept picture. Okay, and then it would have a pretty steep stretch here. So from here you'd go out 1 and then down 3. And then if you went out 2, you need to go down 12. Which would be maybe about here, 1, 2, I don't know, what about here? And here, whatever. Okay. Okay, so here's a quick concept picture of that guy. Okay, so I know where the vertex is now. Now let's do the work to figure out where the focus would be. So remember, to find that, you're going to take 1 over 4p, you're going to set it equal to your stretch factor, which is always on the squared term side. Okay, do what it takes to solve for p. Okay, and then remember that if your p-value is negative, that's just an indicator that you had a negative stretch factor, so that just indicates that, yes, indeed, it did go downward. The absolute value of p is that distance between your vertex and your focus. So focus would be always inside your parabola, and I know that that is more than 1/12 of a unit, but it's hard to draw 1/12 of a unit, so this is just a concept picture. So if the vertex is at the point negative 5, 7, then where would that focus be? So it would have the same x coordinate, but instead of being at a y coordinate of 7, you'd be down 1/12 from there. So what would that be? 6 and 11/12. And then the directrix, it's horizontal, so it would be a collection of points all with the same y coordinate, and it's 1/12 of a unit higher than 5, 7, so 7 and 1/12. There we go. Okay, so we've got focus, or no, sorry, vertex. This is your vertex. This is your focus, and this is your directrix. There we go. Okay, and then the last thing they asked you for was the axis of symmetry, which I think you guys would have probably come in the door with, but I just want to make sure that I'm clear on that. So the axis of symmetry is what would kind of cut the parabola perfectly into two halves here. And so that would be, let's see, that would be a collection of points all with the same x coordinate of -5. So there's your axis of symmetry. There we go. All right, my friends. Hope you're doing all right. Example 3. Find the equation of a parabola that has a horizontal axis of symmetry, that is, a vertex at the origin, and which passes through the point 3,8. Okay, so I am doing this problem because I have seen people get unnecessarily fancy on this one. A lot of people get kind of 1/4p crazy in this lesson, so they keep trying to apply it even when you wouldn't especially have to. So I just want to point out that you'll see stuff like this show up in your homework. And don't forget the things that you've learned in the past still apply. So you could draw a picture of this, I think, pretty quickly if you wanted. So let's think about this. Equation of a parabola that has a horizontal axis of symmetry. So if it has a horizontal axis of symmetry, then which way would your parabola open? I claim it would make it so it would need to open to the right or to the left in order for that to make sense. The vertex is at the origin and it has to pass through the point 3,8. So could you sketch a picture of this if you needed to? You sure could. So said vertex at the origin, it says it has to hit the point 3,8. So let's say this is 3 and let's say this is 8. Okay. And then use the fact that they said it has a horizontal axis of symmetry to know that that would mean that it wouldn't open upward and hit that point. It would open to the right and hit the point. Okay. So do we need to use 1/4p to get this done? I claim no. So you know, I could tell that this is at its core, its parent function would be an x equals y squared, right? Because it opens to the right. And then it's not shifted, so there's no subtraction or addition going on inside your functions. The only difference between this and something that would have to hit the point 3,8 would be a stretch factor. So you could, you know, put your stretch factor, I like calling it A, you know, on your squared term side, and then say, hey, you need to hit the point 3,8. And this is a move that we've used quite a bit where you just force it to hit the point 3,8. So that means when x is 3, your y value would have to be 8. And so your A value would end up being 3/8 squared, which is 64. So what's the equation of your parabola? It would be x equals 3/64 y squared. There you go. Now, let's say you check your answer in the back of the book and they don't have that answer. They could have multiplied both sides by 64 and had an answer that looks like this. I hope you'd know it's equivalent to yours. And they could have divided the 3 over, so another version of your answer would be maybe that guy right there. But I hope that when you check your answers in the back, if they're not exactly the same as your answers, that you at least kind of manipulate them algebraically to make sure that you've got it. All right, my friends, that's the end of section 9.1, part 2. I hope everything makes sense, and I hope that if things don't make sense, that you will send me either emails or comments through Google Classroom to let me know what your questions are, and I will be happy to make help, kind of homework help or clarification videos based on your questions. Take care, everybody.